Hello, and in this video we're going to discuss a fundamental problem in electrical engineering, the RL circuit. First, I believe everyone has a concept of electrical resistance, a long length of wire that impedes the flow of electricity, but inductance is probably not as understood. This is a large inductor. It's a 10 Henry inductor to be exact, having a it's 8.5 Henrys. But a large inductor, roughly 10 Henrys. There's two terminals here, an iron core, and below this paper, there's many turns of enamel wire, similar to what they would use in an electric motor. Let me set this down and we can address one of the most fundamental problems for Circuits 1 students. And give me a second here. Going to discuss something called the RL circuit. Everyone in Circuits 1 or 2 solves this. It's a very fundamental problem. So the symbol for an inductance is this, representing the lengths of wire in the iron core. And we're going to assume that there's an initial current flowing in this direction, and the ideal inductor has no resistance at all. So the current can flow through this idealized path forever, and there's a magnetic field that's maintained here. Now, we're assuming that the switch is initially closed, as shown in that. The question is, what happens when we open it? And the current, instead of going this path, is forced through the resistance here and around back on this path. The results may surprise you. It's very similar to the fundamental RC circuit, which I will cover as well. You may wonder how the current could get started, and in practice you would have like a battery and a resistance which would start it. But we're going to assume that was removed just before. But let's address the circuit. You have a current flowing through a zero resistance path, and you give it a resistance, opening up the zero resistance path, which means it's going to produce a voltage, and the current will drop because energy is being lost as heat from this resistor. What happens? Well, it's a very elegant problem. So we have the voltage through any inductor is always equal to minus L di dt. In other words, the inductor produces a counter voltage that decreases any change in the current. The inductor fights a change in current. Similarly, a capacitor fights a change in voltage, having a almost inverse relationship to this. And we also know that for the resistor, we know V equals IR, or I is V over R. One should note that the I is the same I here, and the V the same V here, because of the parallel combination, which we've stated here. All that matters is this loop here, the inductor and the resistance, assuming that there's an initial current. What happens? Well, intuitively the current dies to zero as the energy is lost from the magnetic field through the resistance, but we have to prove this mathematically. So what one can state is one can take and reach the conclusion that if we divide both sides by R, V over R is going to equal minus L over R di dt. And this is equivalent to I. So it seems we have a first order problem here, but it can be rewritten very similarly as the following problem. We can rewrite this. We can take the L over R and bring it to this side. So we have minus R over L. We can multiply dt on this side, and then that would give us di alone. And then we would normally have an I over here, but instead we divide him over there. So we take the fundamental inductor law and Ohm's law, we synthesize this function and we get this function, which, as you know, we have separated the variables. We've used separation of variables, a fundamental technique for easy differential equations. Now we can integrate both sides, and this would give us minus r over lt would equal ln of I plus some constant. Standard material from any calculus lecture. Okay, so I hope you can follow to this point. It's very simple, relatively rudimentary theory. Now, you may wonder, well, how do we solve for I? You can take both sides to the natural exponent. And then, so we've gone through this step, this would reach the following. So we would have e to the minus r divided by L t, and then that would equal I multiplied by e to the c, where c is a constant. And this is all in the exponent of this. So, based on what we know about inductors, we have to fit the initial condition, which is this guy here. And an inductor can never have an instantaneous change in voltage. I'm sorry, an inductor can never have an instantaneous change in current. A capacitor can never have an instantaneous change in voltage. By the nature of this relationship, if you were to have an instantaneous change in current, you'd have an infinite voltage, and in real life there are no such things. So what we know is that I at 0 is the same as I initial, which is the current flowing initially at time equals 0, I init, before the switch is open and it's forced through the resistance. Nobody really needs to take care at this point of how the current began. Just assume there is an initial current. It's initially flowing this loop, and then you force open the low resistance path, and now it's going effectively through this loop here. Of course, you would need an electromotive force to begin the current. Okay, so what we can do is we can rewrite the final answer to this rather elegant problem. We would have e to the minus r divided by L times t would equal I of t, given that we take and we put e to the minus c over here. But from what I just stated, this value here is I at 0, the initial current. And so we can effectively erase this here, and I'm sorry, I need to get an eraser, and we can put I of 0. And this is the exponential final answer for how the current decreases with time. Very fundamental problem, and it's very similar to the fundamental RC problem. Now, you may wonder, what is the voltage between here, V, when this is opened and forces it through the resistance? Again, this is L and that's R. Well, we can use Ohm's law explicitly, and so it's worth noting we can take the function of IT that we just got and multiply by R, and then that would equal VT. Now the problem is this function is very intuitive. Larger resistance cuts the current faster, larger inductance slows down the current's decrease. Very intuitive. A larger initial current scales the exponential here, where E is the natural number. If we make R too large, the inductor puts a very large voltage across itself, which is very problematic because it can shock you and it can break transistors and other things. But we've solved this entire circuit, the RL discharge circuit, and it's worth noting that resistance is of course measured in ohms with this symbol, and inductance is measured in henries. But typical values are millihenries or even microhenries. The actual henry is like the farad. It's a very large unit. You don't see it often. And you might have kilo ohms across here. So, yes, I hope this problem has been enlightening, and shortly thereafter I hope to cover the RC circuit. And if anyone's interested as to how the current gets started, it follows a similar exponential rule, and I can make another video on that one. Thank you all. I hope this was enlightening.